Hello and welcome to our webinar today on the importance of life of field in flow assurance. My name's Claire and I'll be your host. Before we get started, I'll just run through a few housekeeping items. You should already be able to see on your screen the slides and a question and answer box. If for any reason you can't see these throughout the webinar, you can just bring them back up on the screen again using the dark blue and purple buttons at the bottom of the screen. I recommend that you do maximise the slide screen today, as we will be showing a number of screenshots and diagrams, and all the lines have been muted, so if you'd like to ask a question at any time, please use the Q&A box. At the bottom of the screen, you'll also see a link to our Twitter channel if you want to post a comment about today's webinar, and also a link to our presenter's profile and contact details. We will be running a couple of poll questions to get your thoughts on certain topics, so please take part in them. And lastly, everyone will receive a copy of the slides via email, but you can also download them at the end of the webinar by clicking on the green button at the bottom of the screen, which looks a bit like a notepad. So our presenter today is Alessandro. He is a senior staff consultant with KBC, working in the product management team as a product champion of the multi-flash family of thermodynamic and PVT technology. In his role, Alessandro manages the PVT software and acts as the main interfacial role between research and development and the market, training coordinators, project manager and sales. Alessandro has a master's degree in theoretical physics from the University of Florence and a PhD in mathematics from King's College London. He has 15 years experience in mathematical and computer modelling of multi-phase flows, phase equilibria, phase separation and industrial applications of mathematical and physical modelling, as well as project and programme management. Before joining KBC, Alessandro worked as a product manager and general coordinator within technology transfer and innovation entities linked to the University of Florence. I'll now hand over to Alessandro. Hi, Alessandro. Over to you.
Thank you, Claire, and welcome everyone to this webinar. As Claire just mentioned, the topic of the talk today is the importance of life of field in flow assurance. In particular, we're going to look at a wax deposition case study. That's me, so I'm going to move on quickly to the outline of the talk. I'm going to remind ourselves very briefly what wax is and why and how it deposits. I'm going to look at how one would select a mitigation strategy, and then focus on a waxy condensate gathering system case with various flow assurance issues, look at the life of field simulation results, and introduce our wax deposition solution, FlowWax, embedded in Maximus, to basically answer the topic question: is wax really a problem in this case, and can we draw any conclusion in general on this, and then draw some conclusions on this case. Before I move on, I would like to hand over to Claire for a first poll question.
Yep, thank you. So everyone, you should see the first poll question on the screen. So you just need to select one answer, and the question is: how severe and how frequent are, in your experience, problems related to wax precipitation and deposition? So you've got 4 choices there: very severe but quite rare, very severe and quite frequent, not very severe and quite rare, and not very severe but quite frequent. So I'll give you a few more moments to submit your answers. Okay, so let's take a look at the results. Okay, so that's 100% for the first one, very severe but quite rare. So I'll hand back to you, Ali.
Thank you. Okay, so that's not surprising. Everyone who's attending this talk is considering wax a problem. Most of you, however, recognize that this is not the most common flow assurance problem, and that's precisely my impression as well. So very interesting result to start with. Okay, what is wax? Waxes are crystals formed predominantly of N-paraffins that precipitate out of crude oil as the temperature falls below a certain threshold. Waxes are formed, or crystals are formed, because N-paraffins are less soluble than hydrocarbons, than other hydrocarbons with the same carbon number. So they melt at a higher temperature than other hydrocarbons with the similar carbon number. In other words, they will precipitate before other hydrocarbons with the similar carbon numbers. An important point to always remember is that N-paraffins crystals are not pure crystals, but they are mixtures themselves of N-paraffins of different lengths rather than single N-paraffin species. The fact that wax precipitate from a crude doesn't necessarily mean that they're going to deposit. In order for wax crystals to form, first of all, the temperature needs to be below the wax appearance temperature, which is the temperature, thermodynamic point at which the first crystal of wax can appear in the solution. Typically, a deposit may form in the cold parts of the flow, and the coldest part of the flow typically is at the interface between the flow and the pipeline. However, there must be a temperature gradient across the pipeline for a deposit to start forming. When a deposit does form, the deposit is actually a gel. It's formed of a network of crystals connected to each other and with a very high percentage of trapped liquid. So it's a very porous network with a lot of liquid oil trapped in it. The average density of the deposit, therefore, is not very dissimilar from the density of the liquid itself, which is why it's quite difficult to separate from the liquid overall. In other words, for a deposit to form, two conditions need to hold all the time. The temperature needs to drop below the wax appearance temperature, and there must be a temperature gradient across the pipe. Typically, as the pipe is immersed in a cold environment, like the seabed or in a cold atmosphere, the coldest part of the flow will be at the outer flow, and that's where the deposit will tend to form. Another phenomenon called aging may occur in the deposit as the deposit keeps growing, and as time goes by, a counterflow starts depleting the deposit of oil. So the trapped oil starts to diffuse back into the main flow. And as a result, the deposit will tend to harden and become more difficult to remove from the pipeline. This phenomenon is called aging, and it normally happens at a different time scale from the deposition itself. The typical strategies to avoid the problems associated with wax are normally wax avoidance or some forms of remediation of the wax deposit. To avoid the wax formation, the one thing that one can do is try to stay away from the wax appearance temperature, and this can be achieved by keeping the flow warmer than the wax appearance temperature. So adding insulation to the pipeline, active heating, or in some cases trying to blend the fluid in such a way that the wax appearance temperature drops below the expected temperature of the flow line. In extreme cases, one could inject some wax inhibitors to keep the N-paraffins in solution, although that's not as common as with hydrates remediation. In cases the temperature is going to drop below the wax appearance temperature, and we know that deposit is going to form. Pigging is obviously the most common method for remediation. Of course, the frequency of the pigging impacts on the economics of the project and needs to be predicted accurately and managed well during the operations. In other cases, one might live with it, might live with the deposit and let the deposit grow. But of course, the question to ask in that case is how much deposit can I actually tolerate before it becomes a problem for the production. So in order to select the best mitigation or remediation strategy, one typically would have to ask themselves the following question: is a deposit going to form, and how thick is it going to be? Where in the pipeline is it going to form, and where is it going to be reach the thickest point? And perhaps when is it going to form during the life of the field? And in order to answer all these questions, one will need to have expertise and modeling tools to predict the phase behavior of the fluid to start with, to predict whether wax is going to form, so going to precipitate, how much the wax appearance temperature is going to vary due to variations of the produced fluids or due to other aspects of the production. Is wax going to be depositing along the pipeline? Where and how much is this going to be affected by the plant itself, by the amount of insulation, by the flow rates, the choke opening, and so on. And if the deposit is going to form, how much is this going to affect the thermohydraulics of the plant? How much the pressure is going to drop? How the production profile and the temperature profiles are going to be affected by it in general if we let it grow? And how is all this going to be modified by varying the producing conditions? In other words, for such a complex problem, one would need to have a holistic modeling approach, allowing to look at such a complex problem from the various aspects and the various angles, including PVT modeling, of course, hydraulics, compositional modeling, field planning, and wax deposition predictions. What we're going to describe is precisely our solution based on the integration of maximum flow wax and underpinned by the common thermodynamics of multi-flash to address these problems. And in order to do that, I will go and concentrate on a sample case. This is a high temperature, high pressure gas gathering system with various potential flow assurance problems. It has for sure hydrates problems, potential risk of liquid and water accumulation along the flow line, and because it's a waxy condensate, the potential for wax deposition in the pipeline. Because hydrates is surely going to be a problem, MEG injection is already designed for. Moreover, wash water injection is optimized to avoid scales along the pipeline induced by the MEG injection. The fluid is slightly waxy. Total wax content of 2% has been measured, but we don't really know how that's going to affect the production. What we know is that this field is made of 5 wells. 3 wells are in production at the start of production, while well 4 and 5 are brought in at a later stage. The flow line is 45 kilometers more or less and is running through a seabed at constant 7 centigrade more or less. Because this is an evolving field, one would expect things to change during the life of the asset. In particular, we know that the bottom hole pressure is going to decrease as the reservoir depletes. And we expect the composition of the produced fluid to vary for various reasons, one being the depletion of the reservoir, but also because different wells are going to be brought into production at different stages. Moreover, as the pressure drops, one would expect the flow rate to drop, the temperature in the transport line to drop. So potentially GOR and water cut, but also flow assurance problems may vary in terms of severity during the life of the field. overall, it's going to be quite difficult to select the most appropriate design case unless all these potential sources of variations are taken into account for, which may lead to introducing large design margins just to make sure that every possible worst case scenarios is covered for, or at the other end of the spectrum, one could underestimate risks and incur into potential catastrophic failures in case the flow assurance problems are not accounted for correctly. So let's look at the operating conditions at the start of the operations, just to have an idea of how much and what type of flow assurance problem we're going to have. We've added some insulation in the pipeline, in the flow line, but with a simple simulation of a steady state model, we can see that the temperature at the arrival at the end of the flow line, at the bottom of the riser, is already below the wax appearance temperature and the hydrates dissociation line. You can see that from the diagram on the right-hand side is represented the VLE, the phase envelope, in red, the water line in blue, the wax line in green, and in golden is the hydrates line. The points in brown and the blue point is the choke. The points in brown are the representative for the pipe profile. This is just the subsea segment of the flow line. You can see it's crossing the wax appearance temperature and the hydrates dissociation temperature towards the end of the flow line. This is three-phase flow for most of the flow line. It's all in the two-phase region from the choke onwards, with presence of free water and potential formation of wax and hydrates at the end of the flow line. In fact, if we compare the predicted temperature of arrival, which is around 10-15 degrees, we can look at the amount of separated wax at that temperature. In the diagram on the left-hand side, you can see the wax precipitation curve, which represents the fraction of separated wax in the total liquid. Around 15 degrees, there's not a lot of wax around. It's less than 0.1%, but there is going to be wax in that area of the flow line. We know that we are going to inject MEG, so probably hydrates are not going to be a problem in production, but what will be the best strategy to avoid or to mitigate the risk of wax formation? And for that, we need to extend a little bit, enlarge a little bit our picture of the problem. We know that during the life of the field, the reservoir is going to deplete, so the pressure is going to drop, and one would expect the temperature along the flow line to decrease. Also, one would expect perhaps the GOR to vary in some conditions, but we don't know how much and when and how and why. What we know is that at the bottom hole, the pressure is initially in single phase region. Here on the diagram on the right-hand side, you can see some representative points of the pressure derived from the production profile. This is the pressure at the bottom hole. Is initially in gas-only region, and it drops into the two-phase region at a later stage of the life of the field. So the temperature is going to change, not only because the flow rates are going to change, but also because the amount of gas and liquid in the flow line are going to change. So the heat transfer across the flow is going to vary due to these variations of the pressure at the bottom hole. Moreover, we know that new wells are going to come into production at a later stage, so the fluid is going to change in terms of mix of the phases, because the new wells are going to be brought in a state which is similar to the ones that are in production early on, but when the three wells which are in production right from the start are already perhaps in two-phase region. The composition therefore will change all the time, and then the physical properties of the phases transiting along the flow line are going to change all the time. A simulation based on PVT tables with wax may therefore lead to perhaps wrong conclusions or misleading conclusions in terms of the estimation of the flow assurance problems that we're going to have. So this is a picture at the early life. We can start looking then at what one might expect in the late life. We said that things are going to change. Let's see how much they're going to change. We know that the pressure at the bottom hole in late life is going to be lower than below the 200 bars than it was in the early life. So we can simulate the scenario of the late life, and as expected, the pressure in the flow line, these the two dotted lines are in blue at the beginning of production, and in brown is the end of production scenario, compared again with the phase diagram. You can see that as a result of the depletion of the reservoir, the temperature in the flow line has dropped significantly at the end of the production, and the wax appearance temperature, and as a matter of fact, the hydrates dissociation temperature are crossed earlier on in the flow line than it was at the beginning of production. So from this picture, one would immediately conclude that flow assurance problems are definitely going to be becoming worse as the production goes on. To pick up the correct design case, one therefore can look at, for instance, the amount of separated wax at year 1 and the amount of separated wax predicted at year 9. We know that at year 9, the arrival temperature will be below 10 degrees, around 5 degrees, and you can see from the plot on the left-hand side. From the right-hand side, we can see that the amount of separated wax has more than doubled during the life of the field. So this is more or less the end of the story. We know that the correct design case has to be taken into account the worst case scenario. Pick this late life profile and protect against the flow assurance problem that we will incur in the late life of the field. And this is the end of it, I would think. However, as we will see in a few slides, life is slightly more complicated than this, and in this case, it's actually a good thing. But before I move on, I would like to hand it over again to Claire for another quick poll question.
Thank you. Yeah, so on your screen now, we've got our second poll question. So again, you just need to select one answer. And the question is, how do you currently elaborate your wax precipitation or deposition risk avoidance strategy? So we've got dynamic wax deposition simulations with Olga or LeaderFlow, other wax deposition tools, only wax precipitation and PVT modeling, or don't do any simulation and use some experimental data like wax appearance temperature. I'll just give you a few more moments to get your answers in. Okay, let's take a look at the results. Okay, so we're 100% on the last option, so don't do any simulation and use some experimental data like wax appearance temperature. So back to you, Ali.
Okay, thank you, Claire. And this is actually quite a surprising answer. I wasn't expecting that. I was expecting a fragmentation of answers. Well, that may mean a few things. May mean that we don't trust simulation tools a lot. I'm surprised that that not even wax precipitation PVT modeling is taking into account for wax remediation. But it's a good indication that perhaps a solution hasn't been yet found in the marketplace to rely upon to base the strategies for wax avoidance or wax mitigation. That's very good to know. I hope that after this talk you will have at least a glimpse of doubt that might be a possibility of looking at a simulation tool to do that. I will carry on then, and I've been talking about life of field so far, but I haven't really looked at it at all. So I've just looked at the possibility of simulating the early life and the late life, but I don't really know whether simulating the whole life of the field is going to give me any better insights in terms of the risk of wax accumulation in the pipeline. So I said that per schedule, I've got 3 wells in production to start with. Well 4 and well 5 are going to be brought in later on. I can program that in with the event management in Maximus and make Maximus simulate these events. I also know that the arrival pressure at the platform is initially set at 90 bar and it drops at 60 bar just before the production drops off plateau. And again, I can set Maximus to follow that behavior. The information I have from the reservoir team is a pressure and productivity index profile given by the reservoir expected for the life of the field as the reservoir is depleted. I can program all these in Maximus, run the life of the field, and this is the result of the flow rates for each of the 5 wells. You can see the 3 wells in blue, in red, and green in production right from the start. The black and purple areas are the flow rates of well 4 and 5. On the dotted line, you see the arrival pressure at 90 bar dropping at 60 bar just after about 3.5 years of production. Okay, so this is all good and well, but it doesn't tell me much in terms of the wax or flow assurance problems in general. However, now I have a whole treasure of data, simulated data I can look at, I can pull out. So I can look at the evolution of the temperature at the end of the flow line. This is the blue line that you see represented in this diagram, and compare that with what Multiflash inside Maximus is predicting as the wax appearance temperature or the hydrous dissociation temperature at that same pressure during the life of the field. The green line is the hydrous dissociation temperature, and you can see that as MEG kicks in, the hydrous dissociation drops below 0 degrees C. The arrival temperature is consistently above 5-10 degrees in most of the history of production. So I know the hydrous is indeed not going to be a problem for this case because MEG is taking care of it. In fact, what this diagram is telling me is that perhaps I could reduce the MEG injection a little bit and still maintain a decent margin, security margin against the formation of hydrates, probably. If I compare the temperature of the flow line with the wax appearance temperature, however, things get a bit funkier and a bit more interesting. The wax appearance temperature is predicted to stay constant around 26 degrees C for a long time. But then it starts dropping quite steeply after seven years of production. And eventually, after 9 years of production, the temperature of the flow line, the wax appearance temperature drops below the temperature of the flow line. So this indicates that wax may actually form in the flow line, but only in the first 9 years of production, where the wax appearance temperature is above the temperature of the flow line. While this seems to indicate that in the last part of the life of the field, I'm not going to have any wax problems at all, which is somehow surprising compared to what I was expecting. If you recall what we were saying before, we said that the pressure and temperature are going to drop, so definitely flow assurance problems are going to become more severe as I go along the production. I'm not convinced yet, so I need to dig a little deeper in the life of field simulation to see why this is going on. And I can look at the pressure and temperature profile predicted during the life of the field. The first plot on the left-hand side is the pressure profile in the subsea flow line. I can see the two periods with arrival pressure at 90 bar or at 60 bar. And I don't see anything particularly surprising here. The depletion of the reservoir causes the pressure at the inlet of the flow line to decrease almost linearly. You can see that on the left-hand side of the plot. The pressure remains more or less linear along the flow line, so nothing is really indicating anything strange going on in the flow line. If I look at the temperature profile on the right-hand side, again, nothing seems to be indicating anything odd, apart from the fact that the temperature is predicted to drop, as we saw already from the early life and late life comparison of the scenarios. Perhaps I need to go a bit deeper into the investigation of the properties of the simulation of the flow to look at what's going on. And I can plot, for instance, the profile for the liquid holdup. On the left-hand side here, you can see the liquid holdup along the flow line. As one would expect, as the temperature drops and the composition and the composition of the flow varies, the liquid holdup increases, as one would expect. The only thing that I can notice here is that the profile changes shape in the life of the field. So the liquid holdup the liquid seems to shift along the pipeline in the late life compared to what it was in the early life, but it doesn't tell me again much on the potential for accumulation of wax. However, the compositional is fully the simulation is fully compositional, and because it's running with multi-flash embedded, I can actually look at the separated wax mass fraction in those points that I'm looking at. So on the right-hand side here in the bottom plot, I can look at the separated wax mass fraction along the flow line in the 45 more or less kilometers of the flow line. And here, this plot confirms what I saw before, that the wax, separated wax increases steadily for the first 7 years. You can see that the top line is indicating year 7, and it drops quite dramatically in year 8, and then it disappears in year 9. Mind you, this is not yet the amount of wax deposited along the flow line. I don't know if a wax deposit is going to form. I know that because the temperature is below the wax appearance temperature, some wax is going to separate from the flow, and this is the amount of separated wax in the flow. But whether it's flowing with the flow or it's depositing along the flow line, I'm not sure yet. This is confirming, however, that if there is going to be any problem of wax deposition, it's going to be only in the first 7 or 8 years of production. Later on, I won't have any wax problem. And to have a complete understanding of what's going on, I need to now compare everything with the phase diagram again. Let's concentrate for the moment on the moving profile that you can see, the black dotted line that is moving in this animation here. This is representing the pressure and temperature profile for the whole production line. This is particularly looking at well 1, but it will be similar if we looked at well 2 or well 5. You can see that the part with the higher pressure, which is dropping, is the subsurface part. There's the choke in between, and then the subsea flow line, which is more steady in the lower part of the diagram at lower pressure and temperature. And you can see that as the reservoir depletes, the subsurface part of the production line, so the well, is dropping from the single phase region into the 2-phase region. At some point, the choke is fully open, and the pressure and temperature profile keeps dropping as the reservoir depletes in the late stage. Now, if you focus in at the other lines representing the phase behavior, here is represented again the BLE, the water line, the wax line, and the hydrates line again. And you can see that after the choke opening, the whole phase envelope starts dropping to lower temperature. And with it, the wax line is dropping to lower temperature. So what's happening here is that because I'm looking now at the phase behavior of the composition of the produced fluid and not of the reservoir fluid, the composition of the produced fluid is determined by the mix of the fluids that are being produced by all of the wells. And here I'm looking in particular at the end of the flow line. So here the fluid which is being produced is a mix of all the fluids from all the 5 wells, some of which will be in two-phase region, some will be in single-phase region. Eventually all of them will be in two-phase region. What I would expect then is that the GOR and the water cut of the produced fluid to vary quite dramatically during this life of the field. And what this plot is confirming is that due to this compositional variation, the wax is indeed not going to be a problem in the late stage of the production, in spite of the fact that the temperature of the flow line has dropped quite a lot, by almost 10 degrees in the last part of the production. Now I can gather all this information together and try to picture a consistent picture of what's going on. I can look back again at the phase diagram of the reservoir fluid compared with the pressure drop of the bottom hole pressure. What's happening here is that the bottom hole is initially in single phase region. At some point, the pressure at the bottom hole drops below the inside the two-phase region, below the dew point. At this point, the well starts producing a two-phase system, the two-phase system of gas and liquid rather than gas only. And because the liquid travels with a different speed than from gas, the liquid is left behind, and the produced fluid is presumably becoming leaner as the production goes on. The GOR, therefore, would increase probably, I would expect, during the life of the field. And if I now look at this plot again, and I pull out the GOR predicted at the end of the life of the field, I can see exactly this behavior. In the first 7 years, this is the green line I'm looking at. In the first 7 years, the GOR is almost constant, and then suddenly, just before 8 years, the GOR starts increasing quite dramatically. And this is at the same time as when the wax appearance temperature is starting to drop. So what is happening here is that because the well is producing now a two-phase fluid rather than a single-phase fluid, the liquid dissolves end paraffins better than gas. But because the liquid stays behind, the end paraffins are left in the reservoir with the liquid. As a result, the produced fluid contains less wax than the initial reservoir fluid, and the wax appearance temperature decreases as an effect of the increase of the GOR. So now I've got a better idea of what's going to happen during the life of the field. I can concentrate on the wax deposition study and see whether wax is indeed going to be a problem in these first 7 or 8 years of production, because I know that in the late part of the life of the field, it's not going to be a problem for sure. With flow wax embedded in Maximus, I can select the cases I'm interested in. So I can select the pipe segments in which I think wax might be depositing. I know that the temperature of the flow line is going to drop below the wax appearance temperature only in the subsea part of the flow line, so I can concentrate on that. I also know that the wax is going to separate only in the first 7 or 8 years of production, so I can simulate, pick up the representative cases for from the life of the field collection and run the wax deposition study directly from inside the network model. From the wax deposition simulation, I will obtain information about the required peaking frequency, having set a fixed criterion for it. I will gather information on the wax deposit thickness and its profile. I'm going to have information on the effect of the deposit on the hydraulics, on the pressure and temperature profile. And because the simulation is fully compositional, I will also have all the information about physical properties and composition of the phases and composition at the inlet and outlet of the flow line. And this is the result of the wax deposition simulation. I've run a wax simulation for 4 months in each case. After, at the beginning of production, this is the plot at the beginning of production. The plot at the top is represented the temperature in green and the wax thickness on the colored lines. The wax appearance temperature is in black, is the horizontal line in black. When the temperature, the flow line drops below the wax appearance temperature, a wax deposit starts to form, and it builds up. Indeed, after 4 months, a total wax volume of about 0.2 cube meters is deposited along the flow line. However, the wax thickness, the thickness of the deposit is very low, as you can see from the top plot. And as a result, the pressure drop, which is the green line in the bottom plot, is barely affected by it. So you can see as a very small effect of the wax thickness just in the last part of the flow line, but the hydraulics is barely affected by this little wax deposit, even if it's after 4 months of deposition. We said that things might get worse in the first 7 years because the temperature of the flow line is dropping and the wax appearance temperature is still constant. So we look at year 7. Indeed, the wax appearance temperature is crossed earlier on, before 30 kilometers rather than after 30 kilometers, as you can see from the green line in the top diagram. The wax deposit starts to form earlier on then. It starts around 25, 27 kilometers in the flow line. And the total wax amount deposited after 4 months is more than twice as much as it was at the beginning of production. However, if you look at the wax thickness again, the peak of the wax thickness is not very dissimilar from what it was at year 0, except for that spike that you can see at the beginning of the deposit, which is probably a numerical effect induced by a dip in the flow line profile. So the spike is probably there, but it's probably not as pronounced as it is represented in the simulation. So this is a partly numerical effect due to the dip in the flow line. However, even if the wax amount is more than twice as much as it was at year 0, again, the pressure profile is barely affected by it. You can see that there's a slightly more pronounced effect on the pressure profile by the wax sediment in the final part of the flow line. But again, the hydraulics doesn't seem to be affected almost at all by the wax sediment. I know that things are going to get better after about 7 years. Indeed, if I look at year 8, the condition is very similar to what it was in year 7. So the wax appearance temperature is crossed just before 30 kilometers. The wax thickness is again comparable to what it was in year 8, but the total wax amount has dropped by a factor of 2 again, similar to what it was at year 0. And then in year 9, as I was expecting, the wax deposit has almost completely disappeared. Just after year 9, we know that the flow line, the wax appearance temperature is going to drop below the temperature of the flow line, so wax is not going to deposit at all. And if I look at what's happening in year 9, the wax deposit is barely visible, just in the very last part of the flow line. And I've come to the end of this talk. We have looked at wax deposition problem. We know that wax deposition may represent a severe problem, as you all have agreed at the beginning of the presentation. The potential impact of wax avoidance strategies or remediation might indeed jeopardize the economics of a project if they're not estimated correctly. And an estimation of the size of a problem is crucial, therefore, for the design and for a correct operations management of in presence of wax deposition. However, in order to achieve these, sound thermodynamics and the mechanistic wax deposition modeling is necessary to predict reliably the effect of wax deposition. Normally, wax deposition, wax separation predictions are trusted so little that most operators would just not rely on any simulation approach. We've seen that the life of field simulation allows to pinpoint the real areas and periods of risk during which the production may be affected by the wax deposition. And because this is an evolutionary asset, the effects of variations in various conditions of the production are going to affect the severity of the wax deposition problem. We've shown that having an integrated wax deposition model within the field planning modeling tool offers a major advantage for the elaboration of the best avoidance and mitigation strategy. And in particular, we have shown that what seemed to be an increasingly problematic issue as at the end of the life of the asset, it actually turns out to be a problem which fades away as the production goes on. And even in the areas of high risk in the first 7 years of production, we've seen that the wax deposit is barely affecting the hydraulics of the system. So perhaps this could be a case in which one could live with the wax deposit or peak once in a while just to make sure that the wax is not building up. And with this, I will thank you for your attention, and I will hand it over to Claire if there's any questions.
Yep, thanks, Ali. So yeah, we're going to take your questions now. So if you have any more, please do send them through using the Q&A box. So we'll go to the first question. You should be able to see that on the screen. So how does FlowWax compare with other tools for wax deposition simulations?
Interesting question, Claire. Thank you. It's difficult. It's difficult to say to draw a direct comparison here. First of all, the simulation methods are different, so it's not quite clear how we can compare. Does it specify, Claire? Does it specify anything in the question in particular? In any case?
No, that's just the question.
So So we've done some validation work in the past. The problem is with validation is that not a lot of information is always available. For the cases that we have seen, the FlowWax behaves quite well compared to the experimental results available. Field data are almost never available, and if they're available only in total wax amount, never in wax thickness. So it's always very difficult to know whether the results are actually predicting the correct wax profile. We've done some simulations comparing the results in flow loops. Again, the results are very good, but then the flow loops may not be representative of the real case. However, if there's any interest there, we have some publications. So if you get in touch and leave your contact details, we can send you some publications or some validation studies that we've performed in the past. But it's a very complex question to answer to really. We know that as far as the data available go, FlowWax behave quite well, but we don't know how well and how generally in all the cases.
Okay, I think this next question might actually be in relation to that one as well. So it is saying about giving information on the validation of models and its reliability in real case scenarios. So
yes,
kind of covered that off already.
Yeah, okay. And for the comparison of with other simulation tools, I think the limitation there is that FlowWax is quite unique in terms of the functionalities. So it's as far as I know, FlowWax is the only compositional wax deposition simulation. So to draw a direct comparison with other tools which run on a fixed composition is not always straightforward. What we've seen is that in many cases, FlowWax tend to represent real cases better than other commercial tools that we've seen. It's based on a derived of the Michigan model for wax deposition, and it tends to predict a bit more wax than other wax deposition tools, more comparable with available experimental data, but it's always very difficult to draw a direct comparison between software tools and between experimental or real case data with simulated data. But again, if there's any interest, we've recently supported some research teams that have been carrying out some comparison between experimental data and various simulators, including FlowWax, based all on multi-flash thermodynamics. We can provide some information there if there's interest.
Great. Okay. And our next question coming up. Is there any suggestion on the thermodynamic package to be used for simulations with possible wax deposition issues?
Oh, that's a very interesting one. Thank you. Well, I mean, I'm the product champion for multi-flash, so I would obviously say you need to use multi-flash because it's the best option in the marketplace. This wouldn't be serious, however. So I'm going to step back a little bit from multi-flash and going to try to give a slightly more comprehensive answer there. So multi-flash is using the Coutinho model for wax precipitation, which, as far as I know, is the most refined and most up-to-date wax separation model in the market. However, the various packages in the marketplace have implemented various versions of wax separation models. Some of them require a little bit of tuning from experimental data. Some of them are more predictive, like Multiflash is. Multiflash doesn't require any specific tuning capabilities, and is almost always predicting correctly the amount of separated wax at different pressure and temperature. What I can say is that what we've seen in the past is, in general, the Coutinho model that we adopt treats the wax phase as a non-ideal mixture of N paraffins, while other models tend to modeled as an ideal mixture of N paraffins. This may be a technicality, may look like a technicality, because it's really just an additional factor in the free energy. But if we compare the results between predictions with an ideal system and the non-ideal mixture, like the one in Multiflash, Multiflash tends to predict a lot less separated wax than other models based on ideal mixtures. These might look like a problem in the sense that a conservative approach would lead you to overestimate always the amount of separated wax, but we've stumbled in a couple of cases in which an overprediction of the amount of separated wax was actually leading to a conclusion that the plant was inoperable, because the amount of deposited wax predicted was so much that the plant needed to be pigged every day or every other day. While doing the simulations with Multiflash and with FlowWax, we actually concluded that yes, wax was going to be a problem, but the plant was perfectly operable, and the amount of wax was actually a lot less than initially expected. So again, everything seems to show that the predictions of the separation predicted by wax Multiflash model is correct, and we would suggest to use that. FlowWax has a Multiflash embedded, so that's the choice that we made.
Great. Okay. This next question is slightly related. You might have partly answered it already. So just bring that up on the screen. So what's the difference between the capabilities of FlowWax, Maximus, and Multiflash in wax deposition modeling?
Okay, so these are actually three tools that work together. It's like three instruments playing in an orchestra. So Maximus is a thermohydraulic life of field simulator. So it can simulate the thermohydraulics in the network compositionally based on Multiflash, but without taking into account the presence of deposit wax. It embeds Multiflash, however, so the amount of separated wax in the flow is calculated directly by Maximus. FlowWax used to be a standalone product, is now effectively a component of Maximus. In Maximus, there's a FlowWax object that basically allows the simulation of the wax deposition inside Maximus. And it takes into account the conditions of the clean pipe simulated by Maximus, uses the Multiflash thermodynamics underpinning both software, and calculates the amount of wax depositing in the flow line that one has selected to run the simulation. So it's really, what I've shown is really just one product, is Maximus. Is compositional Maximus with wax deposition, but effectively is three tools working together like a team, really.
Great, thanks, Sally. So we've come to the end of the webinar. If you have any other questions that you want to send through to us, please send them directly through to Alessandro, or you can send them through to us at info@kbc.global. I'd like to thank you all for attending our webinar, and thank you to our presenter. And we hope to see you on one of our webinars again soon.
Thank you.